But the first one's kind of fun. There actually is a suggestion in the write-up that you watch a video of this, but I think you should tell your TAs, Professor Harlow encouraged you to actually just go over and do it. It's easy enough. You just walk over to the the south side of the building, across the lobby again, turn right. All the 4 elevators will have a little force sensor in there, so that measures the upward force on a hanging mass. It's a 750-gram hanging mass, and so as the elevator accelerates, you see that force changes, and you can also feel it. I think it's nice to feel it in your feet better than a video. Activity 2 is just swinging a ball around in a vertical circle, so try not to hit anybody. That's important. And then activity 3 is a little challenging. I did this morning. You set it up so that the situation is in equilibrium. You've got a cart, sort of frictionless cart, sort of like the ones I have here, on an inclined plane. And then there's a pulley, sort of a light little low friction pulley, and a hanging mass. So the hanging mass pulls down, and then there's I guess the component of gravity, which is pulling the cart down the inclined plane, and you try to balance those out. And so you need to measure the mass of the cart, and then try to measure actually with the digital angulometer that angle that you get. So that's kind of a nice measurement to make. And this metal rod, if you unclamp it from here and here, it can fall on your foot. Luckily, I have nice shoes that protected my toes this morning. But probably you guys won't do this, but there is a rule in the labs that you're not supposed to wear sandals in the labs. So I was asked by my technologist to remind you of that. Okay, everybody good? Hopefully we're settling in and comfortable. Let's get into chapter 6 stuff. Okay, so chapter 6 actually opens up with an analogy about conservation laws. Okay, so chapter 6 is basically about conservation of momentum. Chapter 7 is going to be basically about conservation of energy. These are the fundamental sort of underlying principles of physics that we use in mechanics. But you can kind of analogize a conservation law that you might be more familiar with is conservation of mass. So, example, mass of a log on a campfire, and this is one of my favorite shows on Netflix. You just sit there and look at the burning log. Anybody ever watched that? It's ridiculous. It's just hours and hours of just a log burning. Okay, but the idea is that once it reduces to ash, you see that the mass of what remains is much less than the mass of the log that you put in there. But what happens if we choose the surrounding air and a log as the system, then this is again from your textbook, is showing steel wool, which you can burn in a closed flask. If you measure the mass of that inside the flask, it actually doesn't change because there are reactants. When a system of objects is isolated, so a closed container system, its mass equals the sum of the masses of its components and cannot change. It's a conservation law. We can do a quick little, electrolysis. So water is made of hydrogen and oxygen. Talk a little bit about that. But if you separate 18.02 grams of water into its component gases, you get 16 grams of oxygen. How much hydrogen gas? What's the mass of the hydrogen gas that you have to have there? Just give you a minute to click into that. Get things started. Looks like Wi-Fi is responding. I got 240 responses so far, so that's good. Okay. So, going once, going twice. Let's do stop. Let's do laptop 2. So it's off to a good start. 98%. But yeah, the basic idea would be that the mass final equals the mass initial. Since the mass initial was 18.02, the mass final is 16.00 plus the mass of the hydrogen. So the mass of the hydrogen is equal to 18.02 minus 16.00. So that's sort of one way of using conservation law. Initial equals final. That's usually the equation we use, but sometimes there's a delta, so something really does change when the system is not isolated, for example. You say that at 2 different clock readings, so the final is the initial plus this delta. So initial mass mi plus delta m is equal to m final. So that also comes up a lot in all our, so this is called mass accounting. There's this guy, Lavoisier, who discovered oxygen and hydrogen actually long ago. Defined an isolated system as a group of objects that interacts with each other but not with external objects. And when a system of objects is isolated, its mass equals the sum of the masses of its components remains constant in time. So, and this is conservation of mass. So we can always, if a system does not have conservation of mass, that means that our system's not big enough. So if a plate smashes and you take all the pieces that you found and you get less than the mass of the original plate, then maybe one of those pieces went under the oven or something like that, and you have to find it. So we just expand the system. I think that's our conservation law. Now I want to do a few experiments. So let's go to video. And I have 3 experiments that we'll analyze. On the thing. So observational experiment number 1 is you start with a cart which is at rest, and then we send another equal mass cart along to hit it. So at some velocity. Well, that one was supposed to sort of stay stationary. Let's do that again. So they actually repel each other by a magnetic force. Let's do it one more time. Yeah, good. So the first cart goes along with some initial mass. Just before the collision, it's moving. After the collision, that first cart stops, and the second one picks up all that motion. So that's the first experiment. Your book calls it experiment number 1. Experiment number 2 is you load up some mass on the moving cart. I think this is cart A and this is cart B. So this one's now twice as massive, and you give it some speed. And now it really doesn't stop. The other, and also the cart B, the one that gets hit, moves off with a faster speed than that the initial one had. Well, it zooms away. And what's observational experiment 3? 3 is where we actually they have the same mass, and then you have to switch around your Velcro so that now they're sticky. This is a different kind of collision called an inelastic collision when they can stick. And then you start them with velocities towards each other, same velocity towards each other. Oop, not that much. Pretty good. They stick together and they pretty much stop. Anyway, so they were going opposite velocities. When they hit together, they stop. Close enough. So let me go through what that looks like. So this is a new quantity called P, which is momentum. We already used the letter M for mass, so for momentum, we're going to use the letter P. So this is the initial system just before the collision. Just before the collision. So that is when you have the ability to use these conservation laws. Conservation momentum is useful when you have a collision and you're looking at the situation just before and just after the collision. Just after, like just a moment later. Because the collision itself lasts maybe a millisecond or something. So just before to just after that millisecond, the P initial in, say, the x direction is the mass of A times the initial velocity of A plus the mass of B times the initial velocity of B. So A was the one that was moving at 1 meter per second, has a mass of 0.2 kilograms, multiplied times plus 1 meters per second, plus another 0.2 kilograms multiplied by 0. So this whole second term goes to 0 since you're multiplying 0 velocity. It's the cart B starts with 0 momentum, and you say that P initial x is equal to plus 0.2, and it's going to be kilograms times meters per second is the unit. And then if you look at final, what happens is that the B moves off. So P final in the x direction is equal to MA V initial B final A plus MB B V final B. And then this one now has the 0.2 times 0, and this one has the 0.2 times plus 1. So this is, again, equal to plus 0.2 kilograms meters per second. So we find, sort of experimentally, note that P initial in the x direction equals P final in the x direction. So this gives us some idea that between just before and just after the collision, the momentum was constant in time. It did not change if you add the momentum of the two objects. So sort of a new way of solving problems. If we look at the next experiment that I did, it was the same experiment, but I made cart A twice as massive as cart B by adding some extra mass. So in that case, we had P initial x, which is the same thing, MA V initial A plus MB V initial B. This one goes to 0. So it's 0.4 times plus 1. You get P initial x is equal to 0.4 kilograms meters per second. So that's that case. And then this gives you actual numbers. If we had measured it, P final in the x direction is MA V final A plus MB V final B. And you get 0.4 times plus 0.4 meters per second plus 0.2, the less massive one, and it flies off at 1.2 meters per second. They both are traveling to the right afterwards, but with the first one has slowed down and it's transferred some of its momentum to the second one. And you end up with, I got 0.16 plus 0.24, which, lo and behold, is actually 0.4 kilograms meters per second. So once again, we kind of see that the final and the initial are the same, equal. And the last one, well, it's even more obvious. This one's a bit more conceptual, which is that they were going towards each other with equal mass and equal velocity, but equal magnitude velocity, but in opposite directions. So remember, V sub x, it's a vector, right? It has a sign. And momentum is a vector quantity. That's really important. So P initial x is just 0.2 times plus 1 plus 0.2 times minus 1. It's 0. And P final x is equal to 0 because nothing's moving. So this, again, is equal because these things initially had opposite momenta. And when you add the opposite momenta, you get 0. So in all three experiments, you've got conservation of momentum. So that's why when you multiply something's mass times its velocity, you get something that is useful. Because during a collision, it seems to be constant in time across the collision. So we're going to use that to solve a lot of problems in this chapter, chapter 6. Okay. You guys doing okay? Let's go to the next slide. Yeah. So momentum is a property of moving things. I don't know if it's inertia or something like that in motion. So specifically, it's mass times its velocity. And often what I will do, actually, this is equation 6.1 in your book, but I will split it into, this actually means 2 equations in 2 dimensions. Same way, do you remember how we were using Newton's second law? I used to write that as the sum of all the forces in the x direction equals m times ax, and the sum of all the forces in the y direction is m times ay. Same thing. P sub x is equal to m times v sub x, and p sub y and is equal to the mass times v sub y. So if something's moving, it has momentum. Like a moving boulder that's rolling down the hill after you has more momentum than a little stone going at the same speed. That's why we're more afraid, I guess, of a big boulder. It has more mass. And also, a faster boulder has more momentum than the slower one, right? And a boulder at rest has 0 momentum. Do a couple more little calculations. If a 1,000 kilogram car is traveling west at 25 meters per second, what is its momentum? So mass here is 1,000 kilograms. The velocity here is 25 meters per second, comma, west. So the p vector is 25,000. And the units are kilogram meters per second. It's not like, you know how a lot of these units they get a special name like Newton or something? Well, this one, or Joule, this one doesn't have a special name for some reason. I would postulate you could call that the Harlow. A kilogram meter per second would be a Harlow. So this is 25,000 Harlows west. But you can just forget about that. I think I'm the only person that calls it that. So, or a bullet. A 0.1 kilogram bullet is fired straight up, leaves the gun with a muzzle speed of 1,000 meters per second. What is its momentum? Mass here is 0.01 kilograms. Velocity is 1,000 meters per second, up in this case. So P is equal to, turns to be 10. And this should give you kind of a little bit of a feeling of just how dangerous cars are. They carry a lot of momentum. More than bullets even. Okay. So I think I got another learning catalytics question for you. This is about change. So you got a 10 kilogram cart moving to the left at 2 meters per second. You define positive towards the right. So its initial velocity in this direction is negative 2 meters per second. The cart suddenly stops. So what is its change in momentum? A minute to think about it and then pair up and share your answers with your friends, maybe a couple minutes. Okay. Guys had a chance to talk this one over? Maybe I should put initial here. Let's draw a little sketch. V initial X. Going once, going twice, and stop. Oh, not stop that. Stop this one. So a lot of you are answering E. That was the one that I liked. Basically, P initial is equal to negative 20. 10 times negative 2 equals negative 20, whatever Harlow's, kilogram meters per second. And then finally, it stops. P final X is equal to 0. So I mean, delta, another couple ways of doing it. I was talking to some guys who said, yeah, you start with your initial, add the difference, and you get the final. So you have to, or add the change, the delta. The thing that you have to add here is plus 20 to get minus 20 back to 0. Another way of doing it would be to say your delta is always equal to your final minus your initial. So the final is 0 minus 20. So you get plus 20. So you subtract the negative number, you get plus 20 kilograms meters per second. Okay. Let's do another few slides here. We'll continue going here. Now, what's going on with my side screens, Pius? They seem to be both kind of blocked off a little. It's weird. Center one's good, but I don't notice that before, right? Like I don't know if they're bumped. Okay, so we're on 6.2, momentum constancy of an isolated system. So I call this just conservation of momentum. But constancy is the same thing. It means that over time it doesn't change. So you compare an initial situation to the final situation, and you set an equality there. So all those little vectors just mean that there's actually two equations. Momentum is a vector quantity. So really what you tend to do in practice is define an x and y axes, and then you'll say that the x components of all the momentum before and after are the same, and the y components of the momentum before and after are all the same. And so one example, I don't know why there's so many guns and bullets and things in this chapter, but it comes out a lot, is the recoil that you sometimes feel, I guess, if you're shooting a gun, which is that before the bullet leaves the gun, the whole system has 0 momentum. Afterwards, the bullet has some sort of forward momentum because there was a quick explosion which pushed the bullet out of there. But due to conservation of momentum, the system of the gun plus the bullet has to have 0 momentum even after that bullet is fired. And so that's the recoil. The gun goes backwards with equal momentum to the bullet going forwards. And hopefully the gun is much more massive than the bullet, and so its recoil is a much slower speed than the thing. So when a cannon is fired, the force on the cannon ball inside the cannon is equal and opposite to the force. So this conservation of momentum actually comes from Newton's third law. During that explosion, there's an equal and opposite force on the cannon and the cannon ball. And it's over the same amount of time, which is the duration of that explosion, and so they both get the same impulse in opposite directions, and they end up with the same momentum. Opposite momentum with the same magnitude. Okay, same magnitude of momentum, but in opposite directions, so it sums up to be 0. So this is kind of important, and I think I'm going to give you this question just to sort of give you an example of when not to use conservation of momentum. But let's think about a ball which is thrown upwards and comes back down. Is the momentum on the upward flight equal to the momentum on the downward flight, or are they different? Just give you a minute to think about that conceptual question. Great. Yeah, this is a tricky one. Maybe I should draw it out. But first, let's see what you guys' gut feelings are. Can you click in? Give me 5 seconds. 4, 3, 2, 1. So this was what the vote looked like. 84% were voting that it's different. So that is exactly what I was hoping for. The direction is different. And I think some people were pointing out that, in fact, the magnitude is the same. So the question is the difference 0? It isn't. So the way I would sort of draw it, if it went up and down, is that you've got some P initial, upward, and P final, which is downward, okay, with the same magnitude. And so the delta P is going to be P final minus P initial. So if you define plus y is up, for example, then you'd have the final would be a negative number of its p, something like that. And then the initial would be a positive number, 2, negative 2 times the p. So anyway, it's twice twice that magnitude is the difference. So this is an example of when it is not useful to use conservation of momentum. It is projectile motion. I just thought I'd put that out there. This is going to be an example of conservation of energy, because the kinetic energy will be the same before and after, because the height is the same. But it's not a good problem for conserving momentum. Conservation of momentum tends to come into play when you have two objects colliding with a quick little collision, or sometimes an explosion, like a bullet being fired from a gun. Not a lot of situations where momentum is conserved, but enough that it's chapter 6. And it's a good concept. So is momentum conserved for projectile? I think I did ask you this on Friday, if you remember. No. Whenever there's a net force acting on an object, it's continuously changing that object's momentum. So certainly there's no constancy of momentum in that specific case. Okay. And remember, momentum is a vector quantity, so the direction matters. And as I was saying here, conservation of momentum is only a useful concept when you have a system for which the external net forces are either 0 or they are negligible compared to the internal forces in the system. And that's what tends to happen during a collision. 2 cars smash into each other. During that collision, the biggest force either car experiences is the force of the other car hitting it. And so you can conserve momentum just before and just after the collision over a short amount of time. Let's do another. I'm really on to, we'll do 2 on this one, actually. Let's first ask which skater, so there's, I don't know which one's which here. One of these is Paula and one of these is Ricardo. But point being that they are initially at rest. They're on a frictionless surface. So the net horizontal external forces on the system here are 0. There might be normal force and gravity, but they cancel. So they're just pushing on each other. And in the end, after they push off of each other, which skater ends up with the greater momentum? Sorry, I said that wrong. Which skater has the greater magnitude of momentum? Remembering, as I got to remember, momentum is a vector quantity. I guess the whole idea of greater than or less than applies best to scalars, doesn't it? Okay. Ooh, this one's pretty controversial. Going once, going twice, and I'll show you what people were saying here. It's actually pretty much equally split between Ricardo and Paula. Almost identical. Doesn't say exactly, but 18% for both. We really weren't sure. But the answer that I like is both. Idea here being that, so neither. Neither has the greater, is what I'm trying to say. So if this, let's say this guy's Ricardo, and this guy's Paula, what I will say is that P initial of the system is 0 because they start at rest. So afterwards, what will happen is that P final of Ricardo is like negative, and P final of Paula is positive. But P final Ricardo plus P final Paula equals 0 because there's no external forces. So you just say that they're opposites of each other, negative P final Paula. And so if you look at the magnitudes of these with maybe absolute value sign or something, then if they're opposite each other, that means that their magnitudes are equal, so neither one is bigger than the other. Absolute value signs. And do you want to do one more? I don't know if this helps. Is this the same? Oh, not the same. Sorry. The difference is, did anybody spot the difference? So this one, I changed this. So now we're talking about which skater has the greater magnitude of velocity after the push-off instead of magnitude of momentum. Same magnitude. Let's look at velocities here. And going once, going twice. You do take a little getting used to these momentum questions. It's sort of a different way of solving problems. So everyone is voting for Paula here going faster, or not everyone, but 96% of you, which I like. Basic idea here, we already solved that since they have opposite momenta to sum to 0, they have the same magnitude of momentum. And remember that P is equal to mv means that V is equal to P divided by m. So V final of Paula is equal to the P final of Paula divided by the mass of Paula, which is going to be greater than the velocity, I guess since mass of Ricardo is greater than the mass of Paula, implies that the V final of Paula is greater than the V final of Ricardo, just because it's on the denominator there. Does that make sense? What time are we at here? And let's just go back to quickly this one. The idea with all of these conservation of momentum questions is that initial is equal to final. So the initial momentum is 0. So we need the final momentum to be 0 because there was no external forces. There were only internal forces in the system, and those cannot change the momentum of a system. Okay, and that's where you just add it up. P initial was 0 and 0 because they weren't moving. So that equals 0. And final is something they are moving. We know just from the situation that Ricardo will move to the left and Paula will move to the right. And so since they are moving, we say that they're at least moving with opposite momentum. Hopefully you follow the reasoning there. It's a lot different than working with forces. Now we're looking at a system and just looking at what properties don't change. Let's do another question, then we'll work this out numerically. But first let's think of just, imagine that you're out on a boat in the middle of the pond. You see the shore over there, but you have no paddles. But you do, for some weird reason, have a big pile of rocks in the boat with you. So is it possible to move the boat using all your physics skills here? All right, then we can work it out and we should be good. Okay. I don't know if you believe this one happening here, but I'll show you what people are saying. You throw the rocks away from the shore. So why does that work? Well, I think that's because the system of the boat and you plus the rocks has to have 0 momentum. So if you give the rocks a lot of momentum away from the shore, then to compensate for that, you have to pick up momentum towards the shore. Okay? In order for those to be opposite directions and therefore cancel each other and give you the net 0 momentum. So the system ends up with 0 momentum, but you still make it to the shore, which is cool. So let's do it as a problem and figure out some of the numbers here. Laura, whose mass is 35 kilograms, is stranded without a paddle in a canoe that has mass 65 kilograms. So I'm going to just write some of the knowns down here. 35. And the mass of the canoe is 65. And she's 5 meters from shore. She has 10 kilograms of rocks on board the canoe. So there's a third object here, which we'll call the rocks, which is 10 kg. If she throws all these rocks away from the shore and can throw rocks at 10 meters per second, what is the maximum speed she can give herself and the canoe towards the shore? Okay. So the initial situation is that she's not moving. Let's try to draw it here. There's the canoe, and there's Laura, and then there's the rocks. Let's just draw them as a circle. And we can put labels on all these things. These are the rocks, Laura, the canoe. Let's define, if we put a little red line around all of this, I guess. Define the system as being them, and not like the lake or something like that, or the water. Is Laura, the rocks, and the canoe. And V initial is 0 for all of them. They're all initially at rest. So the total momentum of the system is initially 0. So I guess, and then the final situation here will be that you've got the rocks going this way, V rock final, in the x direction, okay, is maybe, let's define plus x is to the right. And so if this is going negative 10 meters per second. And then you've got who's left over here, which is the canoe plus Laura, is going towards the right at V, I don't know, Laura and canoe. In the x final, in the x direction, is question mark. That's what we're trying to find. And let's do the mass of Laura plus the canoe is equal to 35 plus 65 is 100 kilograms. So in the simplify step, you might want to note here, we're going to assume no external forces. No external unbalanced forces. So there are two external forces on this system. One is the force of the water pointing upwards, and the other is the force of gravity pulling everything downwards. But those balance out because the whole system is not accelerating up or down. So there's no external unbalanced forces on the system. So, and I'm going to say that the drag of the water, which is probably not negligible, on the canoe is negligible. And even if it isn't negligible, at least it's complicated, and so we're not going to use it. And I'll show you another way of doing this, which is important. We'll talk more about this next class. But your initial plus your impulse is equal to the final, where the impulse is the change. So if you, the change in momentum is called the impulse. So if you look at x, and you, in this x direction, you look at momentum, what will happen here is that your initial is 0, the change is 0, and your final is going to be the rocks plus the Laura and the canoe. So this is P final of Laura and the canoe, and this is P final of the rocks. What will happen is that, it's a little hard to show here, but if you do green or something, this is what's called a momentum bar chart, which they just use a whole bunch in this e-text, and so I thought I would mention it to you, is that you try to balance things on the bar chart. So if something's 0, it's at the 0 level, and if two things aren't opposite, one goes up and one goes down, they kind of cancel each other out. And so it's a graphical way of looking at conservation laws. Okay, and again, this system here, I should have maybe drawn the system. The system is still the rocks plus the canoe plus Laura, right? It's just that they get far away from each other. So let's keep going here. Represent mathematically would be mass of the rocks times V of the rock's initial plus mass of Laura in the x direction, V Laura initial x, sorry, there's no x, mass plus J, this is the impulse, equals the mass of the rocks times V final in the x. V Laura in the canoe. Plus mass of V Laura in the canoe times V. So you've got 0 plus 0 plus 0 is equal to the mass of the rocks times V rocks plus the mass of Laura in the canoe times V Laura in the canoe final x. So V Laura canoe final x is equal to negative the mass of the rocks divided by the mass of Laura and the canoe times V rocks final in the x direction. So, and that is equal to negative 10 divided by 100 times negative 10. So V Laura and canoe final x is plus 1. That's as fast as she can get it going. And this is towards shore with no drag from the water. So that's sort of how you solve these. And again, there aren't a really wide variety of problems you can solve using this conservation of momentum from chapter 6. If you look at end of chapter, they're all like collisions or explosions or some sort of push-offs like this. But it's enough that and it's a nice way of solving things. So don't forget, hopefully you have some fun in practicals. There's 3 activities. One is, how does weight change in an elevator from a spring scale? The other one is this swing in a vertical circle. And the last one is balancing these this pulley system. Have fun with that, and I'll see you on Wednesday. And please read the impulse momentum theorem. See you then.